The circuit board is quite large and impressive. It's like computer motherboard size. Oscilloscope display, 3 centimeters wide. Vertical resolution. Here is +8 and here is -8 volts. This is sine wave, this is triangle wave. And actually sine wave looks nice at all frequencies. Square wave can have variable pulse width. It has some hidden function, Lissajous or spectrum, wow, or voltmeter. Like I found a small bug. Voltmeter shows 7 volts but multimeter 8 volts. Okay, one more try. This is sine wave, we see a little bit second harmonic. This is triangle, we see third harmonic. And this is square wave. We see odd harmonics a lot. But if I detune pulse width, then we have even harmonics as well. So that's cool. This is cool. Tuner for nodes. Inputs are sensitive to 50 Hz pickup. So probably they all should be connected together. Variable resistor is very sensitive. I can hear up to 11 kHz. 440 Hz. Sine wave, triangle, square. Front panel can be removed, and we see that with surface mount components can make very compact setup. Chips are op-amps, and on output is something stronger. Put op-amp for 556. There are 3 audio inputs, and looks like they are independent and they are coupled through capacitors, and they have very high impedance. If I put just wire in air, 50 Hz are picked up. 2 seconds per division. And on other side, shortest it is 1 millisecond per division. Oscilloscope is based on Raspberry Pi. The second chip is probably analog. On one side we have signals, on the other side we have power supply. With a button USB boot and serial port. Display is bolted with screws, not glued. The circuit of voltage controlled oscillator. Now studying output from button. It can make short pulses for triggering, or it can make long pulses as long as the button is pressed. I don't know what to do with these pulses because they cannot influence the voltage controlled oscillator. It has no input, and there is also no voltage controlled amplifier to use this envelope, so it needs to be built. It became possible to get rid of 50 Hz hum by grounding input 2 and input 3. Play more with the spectrum. Now it is square wave, and we have first, third, fifth, and so on harmonics, all uneven harmonics. But if I change the pulse width, then also even harmonics appear. And if the pulses are really short, we have a frequency comb. A lot of harmonics and equal amplitudes of harmonics. In spectrum analyzer we have peak finder, cursor. This is a sine wave. This is triangle wave. And this is rectangle. And if make very short pulses, we have such comb. It's interesting that square peaks are not clean. There are sidebands. So now I change the pulse V's, and if change the frequency, then the sidebands move. Interesting digital effects. When the frequency is low, we have like a beat note between something. A very interesting effect. Now it is on sine wave, and if I touch the potentiometer, there are some extra oscillations appearing. These tiny peaks which move in opposite directions. Hard to tell. It could be a problem of the sampling, some digital alias problem. Here we have harmonic synthesizer. If I will change the ratio, like pulse width ratio, then even harmonics start to grow, and there is also such complex change of other harmonics which move together. So they synthesize this particular wave. So there is like drop and then increase again. And when the pulses are very short, then we have a lot of first harmonics. Wow, this is cool demonstration. Now we are minimal pulse width and decreasing frequency. And see such nice shapes. There seems to be some faulty connection. If I put hand here, then we have blackout. Actually, it is resistor 470 kilo ohms. When it is touched, it doesn't like, the circuit doesn't like. Now let's play with this button. Short pulses with delay. Oscilloscope can have variable sensitivity, and here I supplied just DC voltage, and we see that noise is about 100 millivolts peak to peak. Oscilloscope looks smooth on sine wave and triangle, but on square waves there is digitalization and jitter. But the frequency is stable. Increase the FFT sample size to 4000. Now we have square wave. Now I make shorter pulses. So we synthesize the waveform shorter and shorter. And when the pulses are short, then all harmonics are equal. But when the pulses get longer, we have such nice function. Now it is square wave. triangle wave. We have odd harmonics, and with sine wave we have little bit from all harmonics, distortions. That's linear scale, that's logarithmic scale. This is sine wave, triangle, and square. Changing pulse width, linear scale, now we have square wave with 50% on off, changing oscillator frequency. These are harmonics for the sine wave. Main tone, first, second, third, 3 or 4 overtones can see a little bit. On maximum sensitivity. Touching circuit board here produces press of the button effect. The oscillator is pretty stable. I touch the op amp and there is no shift in tone. This part of the circuit produces triangle and square. Here is square wave and here is triangle wave. Here we get sine wave produced. There is probably 2 transistor assembly, which it included switches, potentiometers and inputs, and analog components. These wires were bought separately, as well as jumpers, and the oscilloscope was bought separately. This is manual. Manual starts with low pass filter. Here is oscillator, but most interesting is this circuit. I have never seen such before. It's like a drum. And 1 microfarads larger capacitors. Cool feature. Flipping resistor will make it opposite. Cool effect. chaotic oscillator. Oscillator locking. Wow, triangle shapes. Phase changes.